button today. This goes on reducing, and at a certain stage, the stiffness might be so less that it can be almost zero, and that is what is buckling all about. Okay, so that load is understood from this particular buckling analysis. Frankly, there is nothing much out of the way from this point of view, but yeah, this kind of chart can help you understand what is exactly happening, but not much relevance in the sense. Very simple. And if you are getting a positive buckling factor, that means in the load, if you multiply with that load, it is going to buckle. If negative, we are talking about a reversal of load, then it is going to buckle, or else it is not going to buckle. So a more I would say comprehensive way of understanding this is present in this chart, but other round this can be a bit more confusing also. Buckling load factor is more than 1, then we may not see buckling for applied load. So we are also seeing it in that way. When assuming I have applied a load of 10 newtons, I get a buckling load factor of 1.5. That 10 newtons, the part is not going to buckle, but it is going to buckle at a load of 1 point, which is 15 newtons. And on the same lines, other things go. 0, 1, definitely it is going to buckle at applied load. Is equal to 1, at that load it is going to buckle. -1, definitely no buckling unless the load is reversed, and same for the other side of it. So these two are more relevant, which you need to understand. Other things are just indicating you that buckling is not going to happen. But diagnosis, buckle diagnosis, this is fine. Stool is working. Okay. Okay, go back. So I want to quickly show you in the software on what exactly could be the sense or things involved in this analysis. Frankly, nothing much to discuss in this topic apart from what's going to take a bit of time. I would not like to use this. Time will be more on this setup. If I'll stop it. Using a new laptop, and I'm optimistic nowadays on the solution times. They have become faster and faster. No, I would like to use that stool example instead. Let me check if I can open exercise there. This is quite fast. Okay. So over here, the interesting fact is about the way this tool is held at the restraint. This is an interesting thing which you want to understand and imbibe. We mount this tool at this surface, and we can use a fixed condition. But definitely that is not the case in the case of stool. The way it's going to be when it is placed on the floor, it needs to come up. There are different ways in which it could be simulated. One could be a virtual wall as well, or we just apply it and keep it on the floor with some planar displacements being restrained. But the method that has been used in this setup is this one, wherein we are actually putting a remote mass at the CG of that particular surface, the center of that area, and it is being held over there. That is, translations are made 0, rotations are allowed, and that creates an interesting fixture over there. Other buckling happens if such a condition is there. If not, buckling will not happen. We are actually adding to more stiffness, and buckling is restricted. Top 8,900 Newton force is applied, and we can solve it. Let's spoke. Actually, the other setup has ended up finishing. Let me. I thought, yeah, it is done. again, this is using the natural frequency approach itself. As I told you, it is using that eigenvalue and it is checking the force at which the stiffness is becoming 0. Okay, and in terms of results, again, these are absolute displacements, but we are getting the mode shape of that buckling. Typically, this will be near observed. The mode shape will correlate with the natural frequency or the first displacements happening in the body. Okay, so I mean, they will correlate. If you know the natural frequency, you also know direction or the shape in which part is going to buckle. As simple as that. If here you are seeing something called as load factor. So at the moment it is showing a load factor of 21.769. So in all these loads, I can leave aside gravity, but when these two forces are multiplied by 21, there is a possibility of buckling in this part. If not, no buckling would happen. This aside, if I go back to this one, stool buckling, and okay, again here the load applied is 8,900 Newton. The multiplication factor that we are getting is 3.5. So if this 8,900 is multiplied by 3.5, the stool can buckle. You can see shape will be similar to what you see in the how can I do? Similar to what you see in the sorry, I wanted to say similar to what you see in the natural frequency analysis. Convection coming up. Let me check what same with fixture. Yes, the remote displacement, but if you observed the value of the displacement given is 0, but we are holding it or we are applying a fixture. So as I told, there are many different ways in setup. Using this way, you are also understanding how this is going to work. So any other questions on buckling analysis? So in one way or the other, it is actually an extension of frequency analysis, or other way around, an application of frequency analysis, where we apply force and then the critical load at which it is going to buckle. Any question? I'm just scrolling through the training manual to check if there is anything important that I need to discuss. Okay, in 2015 version, we introduced something called as load case combination or load case manager. This helps combine multiple forces or direction of forces into a single, like you can basically play with different studies and come up with a new result which is a combination of these three different studies. Obviously, this is going to be a linear analysis. Frankly, no much study or no much theory involved over here. Apart from we are actually solving multiple studies and coming up with a new setup, which is a combination of all those. While there is a question as well, which I'll answer. In the meanwhile, let me open this assembly so that I have, if necessary, I can trigger the solution. Let me results are around in setup. So in theory or etc., there is nothing much that is there in this setup. So let me check if this is all displacement. Fantastic, the results as well. This makes it easier, but it also has a load case combinations. Oh, yes, not view edit definition. Okay, fantastic. So, but before that, I'll check the question. How to know which mode our part is buckled? It did not have many modes to know. Yes, you're right. As let me open the tuning or tool. Okay, not tuning. Okay, let me take this example. The question is, how do you know which mode it is going to buckle? Now, assuming this tuning fork is there, okay, take the example of this tuning fork. I hold this at the bottom here, right, fixed here, and if I apply the load in the x direction, okay, I think I apply it in the compressed direction. Let me is this fixed? Let me first of all try to find the natural frequency of this body, and I'll take few more, probably 10 more, and solve it. Okay, told you, typically this is a kind of slender structure, and the length is more in the x direction. Okay, and I want to see buckling behavior. I can expect buckling when the load is applied at the top here. Let me try to create a new simulation study. It's a buckling study. Okay, we'll take the support same as this. Okay, much anything on the mesh also. I copy it. Copy the or this and this one doing any force. Okay, let me apply force here. I apply force over here, and let it be 1 Newton, so that the multiplication, typically, by the way, this is what I do. I keep the force normally to 1 Newton, so the multiplication factor that we are getting is actually the buckling load itself. No need multiplying it separately. It is very easy. So doing this, let me solve this. I think to tell us the behavior looks. Okay, take a standard view. Right, we applied it in the x direction. So the buckling is obviously happening in mode shape, which is something like this. So I'm applying, typically is going up. Let's go back there. Obviously, you see this mode shape. Yeah, this is the mode shape. So it is actually the first mode self itself. Typically, the buckling will happen in the weakest direction, and when we do the natural frequency, obviously it is correlating to the first frequency itself. Number 2, shape, I can see it is absolutely matching here. This looks. So will I in Iskandar? If imagine other things, probably difficult this part, but yeah, I cannot. Yes. Okay, look, understood. So I stop it, but yeah, short, I would most of the time expect buckling to be happening in the first mode shape itself. I should not have closed that tuning force scaffolding. Okay. This example, frankly, more of something you can do on your own. There is nothing that I might be required to explain, but all our analysis goes on as it is. As from you should be able to activate this load case manager. This case manager is going to apply diffuse of load through the primary load case. That is, there is a typically force is there, etc. So we can actually go on applying different loads over here, right? Using that. Thereon we have load case combinations. That is, we can actually combine the primary load. So if I applied force in two different directions, I can actually combine it in a certain way. And finally, I want to track the results. I want to see how the this is going to vary. So typically after creation of this setup and I run this, it is help you in coming up with a combination of these things. So few things to highlight. It can be seen as a similar thing to what you saw in design study. Number is not optimization. Now this is it is not going to solve for each of the setups. So it will solve for one setup. Well, after it is going to just results as per the requirement or as per the given combination of loads and boundary conditions, right? So it goes in that direction. It is more time than I expected. I expected it to be very, very fast, but it is solving for certain things. That's okay. So before I move into the next chapter, frankly, I told you there is nothing much to explain here. Not spend more time. I would like to move fast on the next chapter, but any questions, please ask. This is new feature which was introduced in 2015, and that's what is discussed in more detail here. Earlier, that is in 2014, we released one more new feature, which is a sub-modeling. Okay, modeling, and there are different ways of explaining it, but the one that I think is my own presentation explanation. When you go to sub-modeling, okay, so really this is a case wherein I have a setup like this, an entire big setup, and in which we have a certain part. You can see this central part which has comparatively more deflection, right? This has more deflection. This has deflection. And I want to improve the part, or I want to analyze that particular central part in more detail. So what I do, I change the quality of mesh. I change the details of that part, and I want to do more iterations. However, if you do it on the entire assembly, it is going to take a huge amount of time. Instead, I localize on that part. So the process, I have this entire assembly, I can course analysis. On I go into a sub model, and or I go into a local single part, and this part can be further analyzed in more detail. And that is done, I actually come back and see the results on the entire geometry. So we have results with the coarse mesh. Then I go to the component. The boundary conditions for this component can be taken from the global mesh. Then I find on this part, do further iterations, have some holes, change the mesh, do some minor modifications, and go back to the original assembly for further detailed analysis. Sorry, for seeing the results on the complete geometry. This is what sub-modeling is all about. Frankly, is more of a process than more of theory. So nothing much to explain unless you have any specific questions for me. Let me just, I guess analysis is done. No. That's fine. Let's go ahead for the load case manager. Let me check. Okay. The load case manager as well, we are using the same example. Tip for a load case manager, we need to disassociate the small part which connected through a contact set. So it cannot be a part of a body, but it is actually at the contact set, because that is the place where it can transfer the load. Analysis can be done. So the small features somewhere around the part where are the ones where we need detailed analysis. And let's go to that particular chapter. So, can I open the other assembly as well? I think it is with the same name. No, it is not allowed. So I have this. I don't want to wait for another 70% of its solution. It's not allowing me to stop. I start one more version of SolidWorks. Guys, any question on sub-modeling or the first one, that is low? There are new features which are introduced in 2014 and 2015 version. They imbibed as lessons in Relation Professional Training Manual. If you read 2015 training manual, you should be able to see it. If anyone has not the training manuals and if I am coming to your place, please keep me posted. I have ordered a few of the training manuals and I can bring them when I come to you. Let's start, guys. There is a important which is non thermal, or while things go on, I can actually start this chapter if you have any questions. Let me give you a second. Please think. Okay, this appears to be done. Let me check it. Okay. Yeah, we activated the results tab, and uh, this is the way how it looks for a load case manager. So you can see here, the that has been monitored is the overall displacement. The combination of load cases, those are changing appropriately, and that's what you are seeing here. So you see here, even gravity has got multiplied, so you need to be cautious and do the appropriate thing. I can. I will started in one more version of SolidWorks. Hopefully, stop. Yes, I can. I can. Just show you the options. First of all, let's see if there is one more different study. And okay, in here. So let me close this. Save all. Let me open the other study from lesson number 5. Okay, this one. So take a submodel, it is automatically creating a new configuration, and it is going to suppress all other parts and keep only those components that have been used in this submodel, and those parts will be analyzed at the local level. That's it. And I'll quickly show you the place where these options are, uh, and how to proceed. Doing such, waiting for it to respond. Modeling tab, and it appears to be thin topic. Close the other folders which are running also. There are too many things with it. To take time, so obviously here it directly suppressed, and it is showing you this suppressing happens automatically. We not, and all those excluded bodies are put in a folder and they have been represented here. And if I show you the configurations, it's created one more configuration. Okay. Next, let me go back here. Hopefully it is fast. For that, let me stop the other SolidWorks which is trying to start. This is what stop. Get rid of this. Okay, so now it works. While hurrying up a few minutes back, I ended up doing it. Okay, this is the default configuration with all the setups present over here. It is a full static analysis that has been done. Again, because it is to unsuppress all those geometries, activate the configuration and shows this front end. Okay, this way it looks typical simple static analysis has been done. Then on, I can actually create a submodel out of this. unfortunately here I don't know whether I'll be covering it. If you right mouse button click on the study, you should see this option of create modeling study. And whatever may be the reasons, by the reasons are because of the minimum necessity things of this particular thing. So yeah, they are listing down a huge set of limitations. Be aware of that. It comes with its own set of limitations and advantages as well. So of course, you can select the don't show, but nothing in knowing it every time. And when I okay, yes, it is helping me create. So this particular dialog box, where I can select the parts that I want to use for a submodel. So of creating a new one, I'll use the existing one, activate it. And so in study, we have selected those 3 localized parts, which you saw a few minutes back. And certainly nothing much. On 3 parts, you can change the quality of mesh, other details, and do the data analysis. That's it. Else I can explain in this topic. I don't think so, and out of way that involves here. Some submodeling and load case manager. Today as well, so I should not be saying only guys. Guys, any questions? Okay, what is the right time to use or not to use submodeling? So first of all, please be aware of the limitations. Technically, submodeling is useful for assemblies only, not be too much relevant for parts. Obviously, it is assemblies. Third, it is a huge assembly, and you observe the stresses or high level of stresses to be present only in localized components. Okay, only in localized components. So obviously, it is far more relevant for and other way around. You want to do further detailed analysis. You understand if in more detail on that localized components. Then obviously, in cases you need to do submodeling wherein you drill down to that particular local component and understand it in more detail. That's the way it works. That is what is required, and we for as per the necessity. So in many cases the data stresses are well spread out, not to a localized component, so may not be requiring it. Otherwise, it could be cases wherein there is a localized specific component where you see the stresses, but the effect or the stiffness of the entire geometry is equally important. Do not neglect the entire assembly. In such cases, you can do a coarse analysis of the entire assembly to set the stiffness of the assembly. Thereon, on the local component, you can do more detailed analysis. So that should help. That's the process. I'll give more seconds before I jump into the thermal analysis. Questions. Okay, there's a question from Iskander as well. For submodeling, how many parts that we can select for children? Each part only can do analysis for children. No, you can select more than one part. Rather, even in this setup, there are actually few different parts you can see here. 1, 2, 3 different parts. So, limitation, you should be able to select many parts. Nice. It thing as one part would do accurate results. It is the process. If you only that part manipulate, then obviously you want to. But these would be typical cases as that in this one, wherein at the joints where 2, 3 different parts are coming into picture, detail analysis, and those are the ones we want to do that for submodel analysis. So it should not matter whether I select one part, two part, three part for accuracy. Is more on your process on which you want to follow. So typically it would be a big model with beam elements, and only at that localized place you have solid elements, and you want to study the detailed joint behavior. Then in such cases you can actually use big assembly, do it, and then on come to the localized assembly and do a further detailed local analysis. Any other question, guys? And please think on this topic. Any questions, please ask. No questions. Let's move on. One of the most important features, I would say, in this professional training, and this involves a bit of theory as well. So please, give attention to it. Help you understand many important topics which is relevant. Let me check the attend looks okay. Okay, let me go back. So thermal analysis analogy for stress. So this interesting fact has been highlighted in the textbook, wherein we say the analogy between a stress analysis or a setup and a thermal setup. So if you observe, typically the displacement can be seen to be similar to temperatures. That is one of the basic quantities. There is strain, which is more of temperature gradient, wherein it is the variation of temperature across a particular length over here. There are stress, which is for unit area, and over here it is heat flow rate per unit area, which is source, and the loads in thermal would be more of heat source in form of power, or a heat sink, which is moving the heat from a system in form of heat sink. We have prescribed displacements and prescribed temperatures. So displacements are, we are going to either push or pull the part in a certain direction. Temperatures instead are doing a similar thing in thermal analysis. Force are the ones which are giving a bit of flexibility to the body, whereas over here we have convection coefficients or film coefficients which are going to help dissipate the heat from the system, or it could also be heat is dissipated, and the right would be if I have to explain a little bit more, it is more from the solid body, the atmospheric conditions, or from a solid to gas. so that way the heat dissipation happens. We also have elastic modulus, which is which is to thermal conductivity, and that's what it is all about. Okay. Yeah, elastic modulus is a material property. On the same lines, thermal conductivity is also a intrinsic material property. On these terminologies like heat flux, convection coefficient, thermal activity. Okay, fine. Now, a base is more in the way the heat is flowing inside a body. Okay, if I take a simple example, this particular gray part. Okay, observe this gray part. This one, but has a surface which is at a comparatively higher temperature on one end, and on the other end there is one more surface which is maintained at a cold temperature. Now these two maintained by multiple ways, either by convection or you apply the direct temperature. Assuming we have applied direct temperature, then in thermal analysis, the temperature would vary across the thickness, right? Across the thickness, and from thermal analysis, we understand how this variation is going to be. In a sense, I want to see what is the temperature somewhere around here. So thermal analysis will calculate this temperature distribution and show us or tell us the temperature across this particular cross section. That are relevant in such a case, or which show how much heat is flowing, is called as thermal conductivity, which is more of a material property, and we know it for different materials. This is how fast the heat is going to flow across the thickness of the geometry. So that's what it is about. And thereon, the cross section obviously is relevant in this if you want to find out how heat is flowing, or you want to find out the heat flux, the rate of heat transfer. So that helps in understanding how much is flowing across the thickness of the geometry. And finally, this would be obviously per unit length. If it is, it will be seen as a gradient, or if per unit length, then it will be divided by L. So you can, as boundary condition, we are applying the temperature. It will be whatever, wherever in the body. Number two, as a other way around, the other part would be more towards what can I say, the present with the software. Area, that is A and L, are coming from the geometry. E is coming from the material property. Finally, what remains is conduction, which is calculated as a part of the spin. So that's what happens in a thermal analysis, or what is the kind of things that happen inside it. If you want, which I want to highlight, is this particular thing does not happen or is not calculated in the SolidWorks Premium or the simulation standard capabilities. This only in simulation professional. And if you observe now, this is basically the temperature distribution inside a part, or the heat flux, or the rate at which heat is flowing. And whereas in a cell analysis or simulation standard, we are actually simulating only this. So when such a temperature difference is there, or a temperature changes at a certain location, what amount of strain that comes inside the body is understood through this. Materials, as I told you, we do have a list of different materials which with different like this standard database, which you should be able to find it. Even software has it for most of the materials. Okay. Next, this is an interesting thing in the sense, decisions which you are giving to the software. I told you this is a kind of thing will correlated with a restraint, as you saw in the chart. Okay, so what happens is this, which is to atmospheric condition, can dissipate heat to the atmosphere or can even take heat. So if the atmospheric conditions are hotter or colder than the part, then it can actually take heat from the atmosphere. This behavior or this phenomenon is called convection, wherein heat is transferred from a solid component to a liquid component or a fluid body. This, unlike what we saw, the value of or thermal conductivity in the case of solids, that is heat flowing inside the solid, or here the heat is flowing from the solid to the liquid, and that is defined by another constant, kind of constant called as H, or coefficient of thermal convection. Now again, if Z is a constant, T is a surface temperature at the temperature of the fluid, and heat flows or the amount of heat flow is decided by the convection H. Now, unlike for component, H value is not constant to the material. It is a combination of the interface and the boundary conditions involved. If this liquid is flowing at a high velocity, then obviously the value is different. On the other hand, if it is lower velocity, then it is different. It could also natural convection, and the heat transfer happens only because of temperature difference. So all these things come into picture, and actually we can understand how heat is flowing from the solid body to the liquid body or the gaseous body. So this is what convection is all about. By the way, this value of H is calculated after in flow simulation. So flow simulation has the capabilities to calculate the value of H, and H values can be taken to simulation to do further detailed analysis. Coefficient typical values. Yes, these are a few different typical values which can be found on or in different books. Located by bodies in the form of electromagnetics. So radiation. Now this is a phenomenon wherein heat without any medium. That is, we solids, we solids. Finally, heat also flows from a body which is at a high temperature to body at a lower temperature through, I would say, vacuum. And this phenomenon is called as radiation. It is again defined by an equation. There is the constant called as Stephen-Boltzmann's constant. Emissivity would be dependent on the two bodies which are either taking the heat or radiating. It is more of also a geometrical thing wherein we understand how much heat would flow from one body to second body. These are the temperatures. What happened to my mouse? Yeah, these two are the temperatures, and is the area on which it is going. So that again defines how much heat is flowing from one body to the other body, and basically we understand the heat flux or heat movement using radiation. So intrinsically, these are the three different ways in which heat flows from one body to another. That be inside a body, conduction, from a body to a liquid case, convection, and radiation. Or in simulation professional, we are directly giving these inputs in the form of the constants that are discussed in this slide, and it calculates the flux, whereas in flow simulation it has few more capabilities where it does calculate the MVT and other details, whereas in simul we need to give those inputs as a normal property. So I think we are going into the example or the setup. Before any questions, guys, as of now? Any questions? Please think. Any questions? Ask. Looks like oh, there is a question. Okay. Duty transfer. Did not get this question. So, is thermal analysis for finding temperature variation? Heat only. Heat only. I. Tony. Do you mean what could come into picture? No. So, I'm sorry, I could not grasp this question. You want to rephrase it? Then I'll continue speaking. Feel free to write your question again. Thank you. Okay, let me go back to this setup. Nothing. Okay, let me hide the results first. So, typical model with two different parts. There are a few places indicated as strips connect them, and this looks so. Kind of brown parts or the pink parts are actually representing or are of copper, which is having a higher thermal conductivity. You see here, thermal conductivity is 319 watts per meter Kelvin. Okay, this is the conductivity compared to ceramic porcelain, which has a lower thermal conductivity, 149. So it is more of a it is the heat transfer. Okay, so this is the setup. And you here sets would be little bit different in the sense the default contact condition, or if we say it to be bonded, we are saying that there is no resistance to heat flow between two parts, and other way around, then typically there will be some amount of resistance because surface roughness, because of the glue that has been used, because that comes between these two parts. That obviously simulating is difficult, but it can be simulated mathematically using the resistance option that is given in the software. So it could be insulated, wherein no heat transfer happens. So it could be bonded, wherein 100% heat transfer happens. And third, it could be thermal resistance. In the other, this can be seen to be to no penetration contact, wherein heat is moving but with an amount of resistance, and that amount of resistance is given as a value over here. So, in terms of definition, these are the three things for connections. There are, in terms of loads, we have temperature. We can say a certain surface or body is maintained at a certain temperature. That can be forced using option. It could be convection, that is heat flowing from this body to the atmosphere or heat coming from that atmosphere to the body. It could be heat flux, the rate at which heat is flowing from body again to atmospheric condition. Heat power, the amount of heat that is getting generated. Now this could be due to electricity, current, or something that is going inside the body and it creates the heat inside body. And radiation, that is, as we discussed, if you want to simulate radiation effect, then comes into picture. Others are easy. Radiation is a bit more involved with a few more different things which are to be given appropriately. So other two things are far easy. So if you can see here, there is something called as view factor and resistivity. These are two extra things that come into picture. And yes, that's what it is. So let me go back to this example. So one is heat power here. So we are seeing this particular microchip is creating a certain amount of heat, which is 25 watts. And remember, during heat thermal analysis, the appropriate body, typically users end up, even though they know that it has to be, the heat is created by the body, we sometimes do the mistake of holding it, or how can I say, of applying the heat power on surfaces, which is not realistic. So ensure selecting the right bodies or entities for application of things like heat power. Then convections as well. We applying now for these two things, these two surfaces. So remember, unlike heat power, typically convections come on the surface. It is not the body. We select those appropriate surfaces and give the convection coefficients. We are giving the bulk temperature, that is the temperature of the atmosphere around this part, and that is it. Solution is applied in that way, wherein we are specifying the amount or rate at which heat is flowing using the H values, and finally the ambient temperature or the bulk temperature as that mentioned in the software. And apart from that, one important thing which sometimes we miss out is what else? Okay, I think this should be enough. So typically there is something called a steady state analysis and there is a transient analysis. If it is steady state, it is going to do the analysis and give us the results, shows the results which are at the final case. Other way around, if it is a transient, we can see the behavior in the temperature, variation of temperature with respect to time. So we can understand over a period of time how the temperature is varying in a transient analysis. Whereas you can consider it to be final temperature, wherein the entire setup has come to a certain final condition, and we are seeing the the temperature distribution. So this is the way it looks or is. What else? Yeah. Okay. So on doing the analysis, typically we can see the temperature distribution, which is one of the most basic quantities, and the results could be in terms of which can be seen as trains in the body. So in the erection, we can typically it is going to show you the temperature gradient. Frankly, difficult to interpret and may not have much significance. We do most of the times about flux, which will tell you how much heat is actually going out of the system from what location, or how much heat is coming into the system. So flux sometimes are far more relevant than gradient, and use it quite frequently. So observe here, the red areas are the place where the either going in or out of the system at a higher rate compared to other surfaces. So if you want, you can put a fan or something around there would dissipate more heat, or having more um, how can I say, more convection. In terms of, you can see here, more here, as I told you, difficult to interpret or use it at much places. Particularly, this will tell you the higher temperature drop is happening at these locations. So you will understand that basic thing. Temperature. So this is how it looks. Okay, let's go back to the chat window. Did that question come back from Tony again? No, not as that. Is any other questions on this topic as of now? Anyone, guys? Next example is actually on radiation. When you do the chapter, that is lesson 6 as per the training manual, you will also be doing the transient thing. Let me go here. Thermal transient. It should be good. Heat flux. Transient. Okay. So basically will come into picture in case of thermal transient, and we understand the behavior over a period of time. So in simulation professional, only place where we are actually including in the analysis is this clear thing, the thermal transient analysis. In the thermostat option here, frankly much using this, you can, wherever the heat power is applied, that can be controlled based on the temperatures that the part is reaching. So you might be knowing many thermal applications have thermostats which are used for controlling the temperatures of the body in which it is going to work. So if it is a heater, we want to control the temperature of the water that is it is heating. If the water temperature goes above 30 degrees Celsius, then the heater can put off, and other way around. So that kind of effect can be simulated using a thermostat. Okay, should take up these questions quickly unless I find something in or here. Okay. The 3 modes of heat transfer are, I believe now you are comfortable: conduction, convection, and radiation. Open the chat window so that if any feedback I can see. Okay. Oops. Okay, here. The only unknown in thermal simulation is, yes, the input from you. What is the basic unknown in thermal simulation? Question 2, what is the answer? Anyone around? Yeah, I got one answer. Fantastic temperature. It is as simple as that. It's one of the big answers, but I thought I'll give some time. to your attention back. One, while dash is a scalar quantity and has no sense of direction, dash are vector quantities and have x, y, and z direction. So scalar quantity and which is a vector quantity. What about Iskandar? It is a scalar quantity, and heat flux and gradient are more of a vector quantity. Fourth one, heat transfer coefficient is not one of the from thermal simulation studies. Is heat transfer coefficient a result of thermal question? Thermal question. Tony says Alexis is not. So, guys, please understand, heat transfer coefficient is not output from the analysis. It is an input that we can give to the software. So it is a value or a kind of boundary condition that we are giving. Okay. So it is not a result from the thermal simulation study. But if it is flow simulation, we can say yes, it is a result. We can get it as an output from flow simulation. Because not simulating liquids in this study in thermal analysis of this we are doing here, we do not see it as an output. It is not an output. The software does not calculate it. Question 5, heat transfer coefficient required when specifying the radiation boundary condition. What do you condition require heat transfer coefficient to be specified? Which are saying no. So let me go back. Let me scroll through this. So this simple example on thermal analysis, that's fine. Okay, analysis with radiation. Now here the things change a little bit. Let me run this setup directly. So please there is a lamp here which is creating the heat. Luminosity with view factor. Fantastic. So is there you are right? For radiation we need only temperature, emissivity and view factor. Perfect. Radiation. So what is different in case of radiation? So most properties all remain same. This is also same. The type of study that you create is same. It is a steady state thing. You are telling a certain component to be creating the heat. Okay. Now, first of all, this lamp is exposed to the atmosphere. So specifying convection of exposed surfaces and telling the heat can dissipate to the atmosphere through those exposed surfaces, done by the convection coefficient and by temperature. Okay, the atmospheric temperature around the setup. Those two come up over here. Now this is the radiation, and these four are the new options which are going to be used in this particular setup or study. Let's exactly this. If I edit it, really we are telling the surfaces through the radiation is going to happen or going to go out, and the emissivity of those surfaces. Okay, this is one of the things which we specify. One of saying cannot hear me. How about others? Can you all hear me? Can I get one more? Okay, there is another. So if that looks like a local problem at your end, can you please check? Others are able to hear me, so that looks okay. So okay, came back. Good. Surface. Yeah, there are different things. One of them is surface to ambient, wherein we are saying that heat is flowing from the surface to atmosphere. We don't know where it is going; it is just going out, and even that can happen through radiation. Around, it can happen between two surfaces. So we can select the appropriate surfaces. Let me go to the other options that have been done here. So we are, as you say, as a system, are specifying the different surfaces on which the heat is going to move. So here, number one, the heat power is created and is run directly as a heat power source. There on we are telling yes, the radiation can happen from this surface to is around which we have specified radiation to be taking. We are specifying the emissivity of those different surfaces. These conditions have been specified. That's it. So 1, 2, who else is there? 3. Who is 3? This one is small surface array. And this 1, 2, 3. What is the fourth one? 4 is this one. Surface strength. Okay. So see here there are 3 things happening. This is going to create the heat, which is represented by the heat power. Then we have 3 surfaces, 1, 2, and which are absorbing the heat of radiation from that part to the other part. And finally, there is more thing called as the outer surface of the gas, which is exactly in front of it. Even can emit the radiation to the atmosphere. So surface to ambient, and it is radiating from there to the atmosphere. Okay. Of course, even over there we can give the V factor can be to that, and the atmospheric temperature condition. There is a question which says what is an open system. So if you go here, edit, you see this button of open system. So in one way or the other, I can also correlate it or think it to be similar to surface to ambient, or going to nowhere in this sense. Okay. So one, you are saying this what it is created goes where saying the heat is being absorbed. Okay. Other one we can say heat is actually going to nowhere, or it is an open system and it goes to entity which is not similar in this setup. Even that could be the case. We can do that, and we can see, again can see here we are showing the ambient temperature and emissivity, so that can be done. Only difference for ambient, if you see here, we can also give the view factor. That's it. So that, and connection, nothing much. Let me trigger it. So violations, please let me know. We almost at 12 noon. I don't think I should hurry up with the next chapter, which is on thermal stress simulation. I think thermal stress up to the last chapter of or what is now is thermal fatigue optimization and pressure. So these 4 are important topics, and yeah, of course, drop test. So 4 to 5 are the important topics which would remain for tomorrow. Today we saw more of thermal analysis, we saw sub-modeling and load cases, we saw buckling analysis, and the basic thing which is frequency analysis. So this, I would say, more of concept-oriented understanding of all these things. I wish you spend more time practicing these lessons given in the training manual that make you more comfortable with the software front end. But typically, you should be comfortable handling and understanding these things. It is 11:54 now. I have 5 to 6 minutes. I'll be around. Any questions, please ask on any of these topics. that are covered today or in one of the previous sessions. And I think after which I would like to stop for today. We can continue our discussion for simulation professional for rest of the topics tomorrow.